Good morning. Today we are going to start our new module of nuclear physics. In this class, we are going to see the nuclear composition, nuclear properties, and the concept of nuclear electrons. That how the concept of nuclear electrons got discarded. So the basic ideas of nucleus is discussed in today's class. Several models studied the structure of nucleus, and it was Dalton who was the first person who postulated that matter is made up of atoms which are indivisible. So Dalton had said that the elementary particles of matter or the building blocks of matter are atoms, and atoms cannot be divided, or there is no particles inside an atom. But his concept proved wrong when electron was discovered. This model was followed by J.J. Thomson's model, where he said that atom is electrically neutral. So he considered atom as a positively charged sphere with the charges uniformly distributed, so that the electrons are embedded in the sphere like seeds in watermelon. And he also said that this negative charge of electrons is equal to the positive charge of the atom. So the atom is electrically neutral according to J.J. Thomson. But this model has several drawbacks. It's not a stable model because a slight disturbance of the structure will set the electrons into oscillations, and as a result, energy would be radiated out as electromagnetic waves. So energy is emitted as electromagnetic waves. So it's not a stable model. Also, it couldn't explain the origin of spectral lines of hydrogen atom. We know the several spectral series of hydrogen atom as Lyman series, Balmer series, Paschen, Brackett and Fun series. So corresponding to each transition, there will be a spectral line in the corresponding spectrum, and this J.J. Thomson's model couldn't explain the origin of spectral lines of hydrogen atom. Owing to the drawbacks, this model was modified by Rutherford, who studied the scattering of alpha particles from thin gold foils. And he postulated the model of the atom as every atom consists of a tiny central core called atomic nucleus, in which the entire charge and almost entire mass of the atom is concentrated. So it was Rutherford who first gave the concept of atomic nucleus, which is the central tiny core of atom having positive charge and having entire mass of the atom. The size of the nucleus is of the order of 10 raised to minus 15 meter, and it is very small when compared to the size of the atom, which is of the order of 10 raised to minus 10 meter. This model has also several drawbacks, but what he has concluded about the nucleus was perfectly correct. And after these models, several models such as liquid drop model, shell model, collective model, Fermi gas model, true model, etc. have been put forward. Several models, and these models explained the properties of nucleus in a convincing manner. Now, in our class, we are going to study about the nuclear structure. So, our topic is nuclear physics, isn't it? So, it is a study of a nucleus. So, we are going to study about the nuclear structure. So, atomic nucleus is the central core of an atom in which entire positive charge and almost entire mass of the atom is concentrated. As we have seen before, its size is ranging from 10 raised to minus 14 meter to 10 raised to minus 15 meter. In problems, we will substitute 10 raised to minus 15 meter as the atomic radius. Not atomic radius, sorry, nuclear radius. And you know this nucleus is made up of protons and neutrons. For example, ordinary hydrogen nucleus H11 has only one proton. There is no neutron in the case of a hydrogen nucleus. Whereas its isotope deuterium, which is known as heavy hydrogen, represented by H12, in which the nucleus consists of a proton and a neutron. And the nucleus of deuterium is called deuterons. And another isotope that is tritium, that consists of two neutrons and one proton, whose nucleus is known as tritons. Now, what is a neutron? You know that neutron is a neutral particle carrying no charge, and proton is a particle that carries a unit positive charge. And here you can see that mass of neutron is 1.6749 into 10 raised to minus 27 kilogram, and mass of proton is 1.6726 into 10 raised to minus 27 kilogram. So their masses are almost equal. The number of electrons in an atom is equal to the number of protons inside the nucleus, so that atom is electrically neutral. And these protons and neutrons inside the nucleus are together called nucleons. Atomic number of an element is the number of protons inside the nucleus, or it can also be defined as the number of electrons revolving in various orbits around the nucleus, and represented by capital Z. Mass number of an element is the total number of protons and neutrons inside the atomic nucleus of an element, represented by capital A. So you can write number of protons is equal to number of electrons is equal to Z, and number of nucleons, that is the number of protons and neutrons together, is equal to A. So from that you can find out the number of neutrons as A minus Z. The specific nucleus of an atom is called nuclide, represented by XAZ. You know how to represent an element with the help of atomic number and mass number. So the element is represented by X with its atomic number below it and mass number above it. So that is the way in which we represent an element. Now, what is nuclear mass? We know that the nucleus consists of proton and neutron. So nuclear mass is the sum of its constituent proton and neutron masses. And what is a nuclear charge? Charge of a nucleus. It is plus E times the number of protons. You know that this nucleus consists of protons and neutrons. Neutron is having no charge, so only the proton is having plus E charge. And how much protons is there? That much number into plus E. So that gives you the charge of a nucleus, that is plus E times the number of protons. Now what is atomic mass? The mass of the neutral atoms is called atomic mass, measured in atomic mass unit U. So one atomic mass unit is defined as 1/12 of the mass of carbon 612 isotope. Because carbon 612 has an atomic mass of exactly 12 U. So we define one atomic mass unit as 1/12 of the mass of the say 612 isotope. So 1 AMU, which is also written as 1 U, is equal to 1.66 into 10 raised to minus 27 kilogram. And it's the mass in kilogram. Converting it into electron volt, it is 931.25 MeV. How we can convert kilogram into MeV? We will see it later. Now, atomic mass is determined by instruments called mass spectrometer. And there are different types of mass spectrometers. Example are Aston and Bainbridge spectrometers. Now you know that the mass of an electron is 9.1 into 10 raised to minus 31 kilogram in kilogram. Now in terms of atomic mass unit, the mass of an electron is 0.00051 U. And also the mass of a proton is 1.0073 U. Now what is an electron volt? Electron volt is a unit of energy, and it is the energy gained by an electron when it is accelerated through a potential difference of 1 volt. So it is the energy gained by an electron when it is accelerated through a potential difference of 1 volt. So what is 1 eV? 1 eV is equal to 1.6 into 10 raised to minus 19 joule. You have to note it in your notebook that 1 electron volt is equal to 1.6 into 10 raised to minus 19 joule. So this equation will help you to make a conversion from joule to EV as well as from EV to joule. So now you can see how kilogram is converted to MeV in the case of 1U. Consider the mass to be 1U. So M is equal to 1U, that is 1.66 into 10 raised to minus 27 kilogram. What is the energy equivalent of this mass? By Einstein's mass energy equivalence, we have the equation E is equal to mc square. So we have taken M as 1U, substitute M it as 1U, c square is 3 into 10 raised to 8 whole square. So this is what we get the value of energy in joule. And this value can be converted into electron volt by dividing it with 1.6 into 10 raised to minus 19. So we will get the value as 931.25 MeV. So converting joule into electron volt is very important. With the help of equation 1 eV is equal to 1.6 into 10 raised to minus 19 joule, you can convert joule to eV as well as eV to joule. Very important relation which helps you to do the problems. So that's about the basic nuclear composition. You know that these all things you had already studied, that the nucleus consists of neutrons, protons and its masses, its a charge, atom as an atom, electrically neutral, and how 1U is defined and what is electron volt. So these all things I think you had studied in your plus 2 classes. Now how we can classify the nucleus? So classification is based on its value of Z and A as isotopes, isotons and isobars. Isotopes are the nuclides with the same atomic number but different mass number. Examples you can say about a carbon, that is C611, C612, C613 and C614. Here you can see that the Z is the same, so that the element is the same. So whenever the atomic number of an element changes, the element itself changes to a new one. Now isotons are the nuclides with the same neutron number. How we will calculate a neutron number? By subtracting A with Z. So A minus Z give you the neutron number. So C614, N715, O816, F917. In all these cases, mass number minus atomic number will give you 8. So all these nucleides are having same neutron number, that is 8. Remember that whenever the atomic number changes, see, if the atomic number is 6, the element is carbon. If the atomic number is 7, the element is nitrogen. So you have to concentrate on that. Now isobars. Isobars are the nucleides with the same mass number. So C616, N716, O816 and F916. Here in all these examples you can see that A is 16. So they are known as isobars. Now nuclear electrons. Do the nuclear electrons exist? So before the discovery of neutrons, since the atom is electrically neutral, they thought that these electrons are inside the nucleus. So that the atom is electrically neutral since the nucleus consists of equal amount of protons as well as electrons inside it. So they considered electrons inside the nucleus, and these electrons are known as nuclear electrons. And this hypothesis got support by the fact that we know that a certain radioactive nucleus spontaneously emits electrons. So they thought that from the nucleus electrons are emitting, that means electrons must be inside the nucleus. So they thought the electrons are inside the nucleus. So they called them as nuclear electrons. But this concept was discarded by taking several properties. So let's see how the concept of nuclear electrons got discarded. The first point is nuclear size. If an electron is inside a nucleus, it should have an energy of more than 20 MeV. But the electrons emitted from a radioactive nuclei has only energies of 2 to 3 MeV. So that is the first reason for the neglecting the concept of nuclear electrons. Now the second point is nuclear spin. Protons and electrons are fermions with a spin half. So nucleus with an even number of protons and neutrons. Even number means the spins half having even number of protons and neutrons should have 0 or integral spin. Also the nucleus with the odd number of protons and neutrons should have half integral spin. The spin is an additive quantity. So if there are 2 protons and 2 neutrons, half, 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 half. That means adding that you will get 2. That means it will have an integral spin. Similarly, if it is an odd number of protons, just think of 3 protons and neutrons. So half plus half plus half, it will be a half integral spin. And experimentally it was found wrong, that if a deuterium nucleus consists of 2 protons and an electrons, its nuclear spin should be half or 3/2, but the spin observed was 1. So this also proved as a strong evidence against the idea of nuclear electrons. Now the third point is of magnetic moment. We will study about magnetic moment in this class itself. If nuclear electrons exist, the magnetic moment of the nucleus is of the order of the magnitude of that of the electron. But the observed magnetic moment of the nucleus is found to be the order of magnitude of protons. So that's about the magnetic moment, in which the magnetic moment of the nucleus is of the order of the magnitude of protons and not of electrons. Then fourth point is electron nuclear interaction. How the electrons in the atom remain outside the nucleus. That means if there is a concept of nuclear electrons, that is if the electrons is existing inside the nucleus, then how the electrons in the atom remain outside the nucleus. And with the help of the scattering experiments of nuclei and an electron, see, when an electron got bombarded with nuclei, what happens? Nucleus is having positive charge, isn't it? And electron is having negative charge. So there is an attractive force between them. So by studying the scattering experiments of nuclei with an electron, they concluded that this nuclear electrons is not there inside a nucleus. So these are the strong evidences which proved that the hypothesis of nuclear electron is wrong. We had discussed 4 evidences, that is nuclear size, nuclear spin, then magnetic moment and electron nuclear interactions. So with these reasons, the concept of nuclear electrons got discarded. And after that, in 1932, James Chadwick had discovered neutron inside a nucleus. Next, we are going to study about the nuclear properties. And the first topic is size of the nucleus. So, Rutherford had made a calculation about the distance of closest approach a nucleus is turned around by Coulombic repulsion. That means he made a scattering experiment in which an alpha particle is allowed to get incident on a particular nucleus. So what happens when the alpha particle come near to the nucleus? Due to Coulombic repulsion between them, it momentarily stops for a second and turns around. So that is the distance which is known as distance of closest approach, in which the kinetic energy of the incoming alpha particle is converted into electrical potential energy when this alpha particle stops for a second and turns around, due to the Coulombic repulsion between alpha particle and the target nucleus. So its kinetic energy is converted into electrical potential energy at the distance of closest approach. So half mv square is equal to 1 by 4 pi epsilon 0 q1 q2 by r, and it is 1 by 4 pi epsilon 0 q1, that is the charge of alpha particle, that is 2e, into the target nucleus having a charge z into e. We had said that the nuclear charge is plus e times the atomic number or the number of protons. So it is a Ze. So 2e into Ze divided by the distance of closest approach is given as d. From that you can calculate d as Z square by pi epsilon 0 mv square. So Rutherford helped to calculate the distance of closest approach. And consider that we are having the nucleus with a radius capital R, and all the nucleons are inside this nucleus. So its volume is, if R is the radius, we can consider nucleus as a sphere, so its volume is 4 by 3 pi r cube, and this volume contains all the nucleons. So 4 by 3 pi r cube will be proportional to capital A. Now 4 by 3 pi is a constant, so you can write r cube is proportional to capital A. And changing that proportionality, we can write it as R is equal to R0 into A raised to 1 by 3. With R0 as a constant having value 1.2 into 10 raised to minus 15 meter. So this equation is important, since this equation R is equal to R0 A raised to 1 by 3 will help you to determine the radius of any nucleus having mass number A. If you have a particular nucleus with its mass number A, you can calculate its radius with the equation R0 A raised to 1 by 3, with R0 as an empirical constant whose value is found to be 1.2 into 10 raised to minus 15 meter. So the size of the nucleus is specified with its radius, nuclear radius, given by the equation R equal to R0 A raised to 1 by 3. Now the next property is a spin. Nucleons are fermions. So fermions are having spin quantum number S is equal to small s is equal to half. We consider two type of motion for electron, that is orbital motion as well as spin motion. We know that electron is revolving around the nucleus in various orbits, so it is having an orbital motion. Now it has a spinning effect also. Spinning effect means don't think it is like a spinning particle. Spin is a quantum number, corresponds to the degree of freedom. Degree of freedom means the several ways in which a particle can move is known as its degree of freedom. So electron can move in different ways. So we consider that movement as a spin, and it is specified with a spin quantum number smallest, which is equal to half. So due to that spin motion of electron, it is having a spin angular momentum also. Also, due to the orbital motion, it is having an orbital angular momentum also. So this concept of electrons is given to nucleons also, because nucleons are also fermions like electrons. So nucleons are having two types of motion. Spin motion with the spin quantum number s is equal to half. So due to that spin motion, it is having a spin angular momentum capital S, given by root of s into s plus 1 into h cut. So substituting s, the value of spin angular momentum of a nucleons is root 3 by 2 h cut. Now these nucleons have a motion above the center of the nucleus. So that's the orbital motion of nucleons. So it is having an orbital quantum number small l, and due to that orbital motion, it is having an orbital angular momentum capital L, given by root of L into L plus 1 into h cut. Nucleons, I repeat, nucleons are having two type of motion. One is a spin motion and other is orbital motion. Spin motion represented by its quantum number spin s is equal to half small s, and due to that spin motion, it is having its spin angular momentum capital S, which is equal to root of s into s plus 1 h cut, so that the value is root 3 by 2 h cut. Now it is having an orbital motion also, where we consider the nucleons having a motion about the center of the nucleus. So the represented by an orbital quantum number small l. So it is having a corresponding orbital angular momentum capital L, given by root of L into L plus 1 into h cut. Now these two values, capital S and capital L, are angular momentum values. So it constitute a total angular momentum for a nucleus. So the total angular momentum of the nucleus is the resultant of the individual momenta of the constituent nucleons. Resultant of the individual momenta of the constituent nucleons, represented by capital I, which is equal to root of I into I plus 1 into h cut. Now the third property is magnetic moment. Let's consider a charged particle in a closed path. A charged particle in a closed path, a moving charged particle will produce a magnetic field, isn't it? Moving charged particle can be considered as a current, and this current is in that loop. It is a current loop, isn't it? So this current loop acts as a magnetic dipole. We know that in plus 2 classes we had studied what is a magnetic dipole. Two opposite poles separated by a particular distance as magnetic dipole, isn't it? But here we can consider a current loop as a magnetic dipole. So magnetic dipole is having its strength as magnetic dipole moment, isn't it? Represented by mu, which is equal to current into area, in the case of a current loop. But in the case of a magnet, we take one of the poles into the distance separated by that poles. Here we consider a current loop as a magnetic dipole with the dipole moment mu is equal to I into A. Mu dipole moment is a vector quantity. Now current is equal to charge by time. So Q by T, and 1 by T is replaced with the frequency nu. So Q nu A is the dipole moment. Now from Kepler's law, we know that dA by dt is equal to L by 2M. From that you can take dA is equal to, then you can integrate it to find the value of area. So A is equal to L by 2M into T, again 1 by T as nu, so L by 2M nu. So you got the expression for A. So substituting A in mu, we will get mu is equal to QL by 2M. And we had found that L is equal to root of L into L plus 1 into h cut, that is the orbital angular momentum, which is also a vector quantity. So we got the value of dipole moment mu as QH cut by 2M into root of L into L plus 1. And here you can see that Q by 2M is a constant, so it is known as gyromagnetic ratio. And in the above expression you can see that this dipole moment mu or magnetic moment is directly proportional to angular momentum L. That means this angular momentum gives rise to magnetic moment mu. And we had just considered it as a charged particle, isn't it? If we consider that charged particle as an electron, how we can write mu is equal to EH cut. Q is replaced with E and M is replaced with the mass of an electron. So EH cut by 2 ME into root of L into L plus 1. Now what is EH cut by 2 ME? EH cut by 2 ME. It is a constant. H cut is simply H divided by 2 pi. So we replace H by 2 pi as H cut. So EH cut by 2 ME is a constant which is known as mu B, that is Bohr magneton. So how you can define mu B from the above equation? Mu B as the ratio between magnetic dipole moment and the magnitude of angular momentum. See, we had write L as root of L into L plus 1 into h cut, isn't it? This h cut is considered as a unit of angular momentum. So what is the magnitude of angular momentum? It is root of L into L plus 1. So Bohr magneton mu B is defined as ratio between magnetic dipole moment and magnitude of angular momentum. Now we are giving that concept to our topic, that is nucleons. So nucleons also possess orbital quantum number L and spin quantum number S. So there are two magnetic dipole moments for nucleons, that is mu L and mu S. Since the nucleons are having two types of motion, corresponding to each motion there exists a magnetic moment. So mu L and mu S is given, and here also you can see that EH cut by 2M. There is a constant. That constant is known as nuclear magneton. In the above slide we had seen that if we considered it as a if we consider the charged particle as an electron, we had found that the constant EH cut by 2ME is the Bohr magneton. Here it is EH cut by 2M, where M can be mass of the proton or mass of the neutron. We know that the masses of proton and neutron are approximately equal. So EH cut by 2M is mu N, that is nuclear magneton. So you can just divide mu B by mu N. But you will get a constant value, and that value is 1837. So that's about the nuclear magnetic moment. And the last property, that is magnetic energy. So we know that this nucleons is having a motion inside the nucleus. Due to that, we can consider it as a current loop, or we can consider it as a magnetic dipole with a particular magnetic dipole moment. If we consider this such a dipole placed in a magnetic field B, so what happens to its energy levels? We are going to check out how the energy levels changes when we place such a magnetic dipole in a magnetic field B. Here you can see the dipole is represented with an slanting arrow with the dipole moment mu, and this dipole is making an angle theta with the magnetic field direction. So, when a magnetic dipole is placed in an external magnetic field at an angle theta, a torque began to act on this dipole given by torque is equal to mu b sin theta, or you can write it as mu cross b, or you had studied it as m cross b, where m is the dipole moment. Here tau is equal to mu b sin theta. Here we are going to find out the magnetic potential energy of the nucleus. How we will find the magnetic potential energy? We must first establish a reference configuration in which um, that is the magnetic potential energy, is 0. So we consider at theta is equal to pi by 2, um is equal to 0. That is, mu is perpendicular to B. When mu becomes perpendicular to B, what happens? You can see that when mu becomes perpendicular to B, theta becomes pi by 2, isn't it? And we make a reference point that at theta is equal to pi by 2, um is equal to 0. Now, what is potential energy? Potential energy, you know that it is equivalent to the work done. So, here the potential energy is equal to the external work done to rotate the dipole from theta is equal to pi by 2 to any angle theta. So, we had made a reference direction that theta is equal to pi by 2, and we are rotating the dipole from theta is equal to pi by 2 to a particular angle theta. So, for that we should do work, and that work is stored as the magnetic potential energy. So, um is equal to integral pi by 2 to theta tau into d theta. So, integrating it, you will get minus mu z b cos theta. Why I am giving mu z? That gives you the z component of magnetic moment. Or we can say that if mu z is in the direction of B, the angle between them, theta is equal to 0. So, cos 0 is equal to 1. So, um will be minus mu zb. That is the minimum value of magnetic potential energy. If mu z is opposite to the direction of B, cos theta will be 180. So, cos 180 will be minus 1. That is, um is equal to mu zb. That means maximum value of magnetic potential energy. So, what happens when such a nucleus is placed, or magnetic dipole is placed in a magnetic field? Each angular momentum state of the nucleus is split into components. So, this is the magnetic energy gained by the nucleus when it is placed in a magnetic field. So, what happens here? You can see the second diagram in which there is a dotted line making a partition between B equal to 0 and B greater than 0. That means if there is no magnetic field present, what happens is that the nucleons is having a particular energy level given by E0. Now, what happens when such a nucleus or nucleon, proton or neutron, is placed in a magnetic field? When it is placed in a magnetic field, it attains a magnetic potential energy mu pzb, which we had seen earlier. See here, mu z into b. If you are considering proton, we can write it as mu suffix p z b. So, here we are considering a proton in an external magnetic field. So, its magnetic moment is given by mu p z. So a given energy state E0 is split into two energy levels. One energy level is having a higher energy than E0 and another energy level having lower energy than E0. And when a proton is placed in such a magnetic field, it can have an magnetic potential energy mu pzb. So it is having a lower energy level E1 with energy E0 minus mu pzb, or it can have a higher energy level E2 which is equal to E0 plus mu pz into b. So that the difference between the splitted energy levels is given by E2 minus E1 which is equal to 2 mu pzb. The lower energy state is known as the spin up state and the higher energy state is given as spin down state. So always the proton will try to reside in the lower energy state when there is magnetic field. Now when the proton attains enough energy, that is 2 mu pzb, it will excite to its higher energy level E2. Also, when it loses its extra energy 2 mu pzb, it will come back to its lower energy state. And this phenomenon is known as NMR, that is nuclear magnetic resonance. So, when a proton or neutron is placed in a magnetic field, its energy levels got splitted with a higher energy level and a lower energy level, and the transition between these two energy levels takes place when sufficient energy is emitted or it is absorbed, and the energy difference between these two levels is given as delta E, which is equal to 2 mu pz into b. So you already know that by Planck's law E is equal to h nu, isn't it? So 2 mu pz b is equal to h nu. Then what is nu? Nu is 2 mu pz b by h, and this frequency is known as Larmor frequency. That means if a photon get incident with if a proton get incident with a photon of frequency called Larmor frequency, it will attain an energy 2 mu pzb and make a transition between these splitted energy levels. So this phenomenon is known as nuclear magnetic resonance, and Larmor frequency nu is equal to delta E by h, which is equal to 2 mu pzb by h, is called Larmor frequency, and it is the frequency with which a magnetic dipole presses about a magnetic field. See, here you can see the direction of B vertical, isn't it? And the mu is making a cone shape movement, and such movement is known as precession. And you can see the nucleus below it, and the dipole moment is having a slanting direction. This mu presses around a magnetic field, and that frequency is known as Larmor frequency. And this is what we had studied, nuclear magnetic resonance. If we put a sample of substance that contain nuclei with spins half in a magnetic field, the spin of most of the nuclei will become aligned to be called spin up state, because this is the lower energy state. If we apply electromagnetic radiation at the Larmor frequency, the nuclei will receive the right amount of energy and will excite to the higher energy state, and this phenomenon is known as NMR, nuclear magnetic resonance, which help you to determine nuclear magnetic moments experimentally. So it is one of the applications of NMR to determine nuclear magnetic moment experimentally. There are two ways in which we can achieve this NMR. Either you can place the proton or neutron in a non-magnetic field and can give several electromagnetic radiations with the frequency varied, so that on attaining Larmor frequency there will be a transition between the splitted energy levels. Or you can give exact Larmor frequency radiation to the proton, and you can vary the magnetic field so that on getting appropriate field there will be a transition between these two states. So that is the two different ways in which you can attain NMR. So knowing Larmor frequency and B, mu can be calculated. So to determine the magnetic moment experimentally is one of the main applications of NMR. Now there are two uses to study the chemical structure, and also in medical field we are using NMR but with a different name called MRI. This NMR is known as MRI in medicine. You know MRI, it is magnetic resonance imaging. So it is used for imaging in medicine, and it is having higher resolution than X-ray, and it is more safer than X-ray. In order to avoid the frightening term nuclear, the term NMR is replaced with MRI. So that are the uses of NMR. So I know this is a lengthy session for you, but still, so all topics are of a smaller duration. So make a note of this, and for any doubts you can contact me in WhatsApp. Thank you.